to see you and discuss with you. Okay. So today I'm going to talk about our recent paper on quantum network state. Yeah, the title is a little bit long, so it's Symmetries in quantum network lead to no-go theorems. Theorems for entanglement, distribution, and two verification techniques. Entanglement. So this paper is a little bit long, but so today we only talk about the main ideas of this paper. Firstly, we know that in quantum mechanics, one main problem is about whether a state is separable or not. If we have a bipartite system, for example, we have A and B, and if we say a state is separable, if there is a hidden variable lambda such that the whole state can be written in this way. For given hidden variable lambda, it happens with some probability p lambda, and then we will have the product state, 0a lambda and 0b lambda. Okay. If there is some bipartite state without such a decomposition, then we say that the state is entangled. Bipartite. Okay. Sometimes we just call the entangled state an entangled pair. Okay. Like in quantum communication tasks, we could have entangled pairs shared between different parties. Like in this way, we have 3 entangled pairs, and we have 3 parties, A, B, C. For example, here we have the entangled pair. Let's just denote it row A, and row B, and row C. So row A is an entangled pair. It's shared between party A and party C. Row B is another one, and it's shared between A and B. Row C is another one, which is shared between B and C. Besides that, we each party, after they have received the particles, they can apply some local channels on those particles to prepare the state. Okay. Maybe we can denote it as EA, EB, and also EC. So besides that, there could be some classical random variable lambda. And for each lambda, we would have the entangled pair, and also have the local channel, which depends on this classical random variable lambda. Okay. If we have such a triangle network, and if we can prepare some state, tripartite state in this way, then this kind of state is called triangle network state. And generally, we could have some other more complicated networks, and we will have the state from that network. Yeah, we call it a network state. As we can see, usually it's quite complicated to draw the network in this way. So sometimes for simplification, we just draw it in this way. This means that we have the triangle network, and each edge just represent one source. And for example, this edge, it has 2 vertices. It means that it will send 2 particles, and each particle to one party. Okay, it's just one representation of this network. And so for this one, we would call it a triangle. And similarly, we could have a square. Okay. Yes, and for row A, row B, and row C, maybe we will call them source, and for each party, sometimes we just call them receiver. Okay. So as we can see, if we have those kind of quantum network and we prepare the state in this way, we can prepare some genuine multipathetic entangled state. Let's say if each edge is just a Bell state, each edge just represents a Bell state, and then we apply no local channels. So each party has 2 particles, and in total, we have the 3 Bell states shared between those 3 parties, and it's a genuine tripartite entangled state. Okay, but one main problem is that what kind of state can we generate in this way in a quantum network? As we can see, there is an advantage to generate the state in network, because we only need the entangled state, which involves less parties, to give us the entangled state which involve more parties. Okay, but can we generate any state, or what kind of state can we generate in this way? Okay. So there is one important technique when we talk with the quantum network state. It's called inflation. So what does that mean? It means that we just make a copy of the sources and also the receivers, and then rearrange them in some way. We will have a look at some inflations. For example, if we have this triangle, okay, yes, we have 3 different colors. Okay. Yeah, almost the same color. Anyway, we have 3 different colors. Yeah, thank you. So let's say for the triangle, to make it more clear, we use the white to represent the row A, and we use right, row B, and also brown, row C. Okay, this is our original network. Now we could have some inflations, like we have row A, and then we have row B, Then we have row C, another row C, row A, and row B. This is the one inflation. So here we have original A, B, C. Here it's A, B, C, and A prime, B prime, C prime. So as you can see here, we have two copies of the same source state, and also two receivers, and they are equivalent to each other. In the sense that if we consider the marginals, for example, the marginal state which belong to Alice, which belong to A, and the marginal state belong to A prime, they are the same state. Yeah, okay. And also that if we, in this inflation, if we consider the marginal state on AC, it's the same as the marginal state on AC in the original network, because we have the same. It's better to draw it in this way. So this is the source state for shared between A and C. Except that, as we can see, in the original network, we have another particle for Alice from the source between A and B, and we also have another particle from the source row C between B and C. So this is in the original network. As you can see, it's the same. It's same in the inflation. We also have the same state, or the same particles. We also have the same channels. That's why the marginal state on AC in the original network, and also is the same as the marginal state on AC in this inflation. So similarly, if we consider the marginal state on A prime and C prime, it's the same as the marginal state on AC in the original network. Okay, so as we can see, we have a lot of marginal relations in the between the original network state and the network state after the inflation. Okay. In fact, we could have another different inflation. It would be like this. So yeah, without a loss of generality, we still denote it A, B, maybe C, C prime, A prime, B prime. So as we can see, if we have a look at the marginal state on A and C, if we look at the colors, maybe the color here it's not so obvious, but as we can see, the source state for between A and C is same as here, and also another particle for C, another particle for A is same as in the original network. Besides, they have the same local channels as in the original network. So we still have the marginal relation between the original network and this network. Besides that, we also have something like, maybe let's just call it tau, and we call this state gamma. We also have gamma AB equal to this state rho, equal to rho AB. Also gamma A prime B prime equal to rho AB. So we can check that for any bipartite, I mean, for any age in this inflation, if we consider the marginal state, we have some correspondence in the original network. Okay, as we can see, we have.
Sorry. So in the last one, you have more than that, no? Because you have marginal states now between primed and unprimed observers, which you don't have in the original one. So in your tau, there's a marginal state between C and B prime, where they share an entangled pair, where in the original one, there is no such entanglement between C prime and B, no?
You mean here, C prime and B?
Yes. So in your diagram, C and B prime, they share an entangled pair. Yeah?
Yes.
But there is no such thing in the original one.
Okay. So in this case, we would say that gamma B C prime is the same state as rho B and C. So I mean, although we have different labels, but the state, they are the same state. Mathematically, they are equivalent to each other. If we only consider the sources and the other particles and also the local channels, I mean, they are equivalent in this sense. So for example, here we have if we have a look at here, it's rho C between B and C, except that there is a white particle for C, there is a red particle for B,
Yes.
and we have the local channel for B and the local channel for C. And here, okay, we have the source state rho C for B and C prime, although it's called C prime, and another white particle for C prime, another red particle for B, and also the same local channels. Okay. So in this sense, as we can see, we have the same particles and also the same channels. That's why those two states, they are equivalent to each other.
Okay.
Yeah. Yeah, because I mean, we have different copies of the original parties. That's why we won't have sometimes we won't have the same labels. Here we must have A and A prime.
So for you, A and A prime are the same thing. It's just like they're copies of each other.
So if we have a look at the marginal state on A and A prime,
they will be the same.
Yes, yes. But sometimes, yes, those two inflations are special. Sometimes maybe, let's say, we could also remove. Yeah, we could also make some other complicated reflections, such that maybe for A, we can keep more marginal relations, but there is not so many marginal relations for A prime. It depends on the inflation. For example, in this inflation, if we have a look at the marginal state tau ABC, it will equal to the original state rho ABC.
Yes.
But here, if we have a look at the marginal state gamma ABC, it's different from the original state rho ABC. Because yeah, B and C, yeah, okay. Okay, so from my personal opinions, I think those kind of technique to make use of many copies has been used a lot in quantum information theory. For example, when you consider whether a state is entangled or not, sometimes we make use of 2 copies or many copies, and we consider some marginal relations. I think Miguel is more experienced at this. Yeah. And also in quantum metrology, if we have more copies, and we can have a better estimation of the parameter. And also in NPA hierarchy, although we do not have many copies of the state, but we have many copies of the measurement. And maybe in each copy, the measurement has different marginal relations. Yeah. Okay. But if we only have this inflation technique, there could be some difficulty to apply this technique. So yeah, here I would like to refer to one paper from Miguel. It's PRN. So in that paper, they have done some inflation of the state rho in the triangle network to have those two kind of inflation, tau and gamma. Okay, they have this state. And there they have considered that for each source, we only have, for each source, I think, for each source, we have 2 qubit entangled pair. And thus, in total, we have 6 qubits. If we, I mean, yeah, here we have, sorry. Let's just make it simple. Yeah, please correct me if I have mistaken something. Let's say that if in the original network for A, B, C, each local system is just a two-dimensional. I mean, maybe here we have 2 particles, and after we have applied the local channel, and it will give us a two-dimensional system. Then in this case, we will have, in the original state rho, we have 3 qubits. And then in the inflation, in each inflation, we have 6 qubits. If we have 6 qubits and we want to have the density matrix, then the dimension would be of this matrix would be 64. And then if we want to consider we have such a matrix, so it's a semi-definite, and we make use of some SDP techniques, and we consider those marginal relations. They are just linear conditions, so we still have SDP. Then, then we can try to use this technique to tell whether some state can be from this network or not. Okay, if you are interested in this technique, you can just have a look at this paper. There are many interesting results. And in fact, in that paper, they have also mentioned that if we have the local dimension for A, B, C is not 2, but 3, we have 3 qubits. And then we have 6 qubits. And then here it will be 3 power 6. It's okay, so to do such an SDP with the matrix in this dimension, it's very hard. It's very hard. Yeah. So then it means that if we want to consider more complicated networks, then we need some other techniques.
Maybe a quick question. So the local channels in the inflated scenario, you add the copies. So for example, there would be a channel for the A node and another channel for the A prime, and this would be a tensor product. Or
yes,
would be one.
yes,
Okay.
they should be tensor product. But okay, I forgot to mention that. So let's say if here we have the classical random variable lambda, and in the inflation, we only have the same. We only have one. We do not make a copy of this classical random variable. Yeah, it means that for each classical random variable, we make a copy of the source state, rho A lambda, and also the channel, yes, EA lambda. Okay. Yeah, as you can see here, in the inflation, we have different copies of the same source state, and also different copies of the parties of the nodes. it means that we have some symmetry, correct? We have equivalence, we have some kind of symmetry. And the symmetry is more about the structure. I mean, as you can see here, it's difficult to do the parameterization to consider the state explicitly. But could we just consider the structure without going into the details? This is our initial idea. Then, I mean, so the idea is that we want to consider symmetry and consider the structure. What kind of state are good candidates? So one is that the graph state. Don't worry, I will explain this concept later. And another one is the symmetric state. Okay, so in this paper, we have mainly considered those two kind of states, whether they can come from whether they can be from some network or not. Because they have some symmetries, and in the inflation, we also have some symmetries, and then we can combine those symmetries with the inflation technique to have a look at whether this kind of structure or topology can give us those states or not. Okay.
Can you keep it close, because otherwise the camera. Can you erase this and use
Okay.
this, or you need this? Well,
I can use. I can use this one. Yeah. Thank you.
Yes, just maybe don't write here.
Don't worry. Yeah. Okay. So how much time do I still have?
Let's say
20 minutes.
Yes. Okay, let's say.
Okay, then let's first talk about the symmetric state. So, yeah, symmetric state and antisymmetric state. Okay. So let's have a look at the Barrett case. We could have the flip operator such that it will map the state ij into the state ji. So they are just a pure state. And then we could know that FAB just equal to this operator equals to its own complex conjugation, and also FAB square equal to identity, except that we could have identity plus FAB over 2, and also identity minus FAB over 2. They are just projectors. Correct? So maybe we can denote the corresponding subspace for them as S plus and S minus. And for any state in rho in S plus, we call it a symmetric state. And for any state rho in S minus, we call it antisymmetric state. Okay, so as you can see, if we have a state rho in S plus, a symmetric state, and if we apply the flip operator FAB on one side of rho, then we would have the same state. If we have a state in S minus, which means that it's antisymmetric, then we would have SAB rho equal to minus rho. then we could also consider the multipartite symmetric state and also the multipartite antisymmetric state. What does it mean by multipartite symmetric state? It just means that I will just give one example. If we have 3 parties, A, B, C, then we would have 3 flip operators. Okay, if the state rule under the axiom of any flip operator just equal to itself, then we see that this state is symmetric. If for each operator it will give us a minus sign, then we see that it's antisymmetric. Okay, then we would have some properties of the symmetric state. The first one is that if this symmetric state is a mixed state, then we would have it to, we can decompose it in this way. Then if rho is symmetric or antisymmetric, we would have phi I to be symmetric or antisymmetric for any I. So this is easy to see because according to this definition, if rho is in this subspace, of course, any state in its decomposition should be in this subspace. Okay, and also, yeah, for the antisymmetric case. So maybe we'll call it lemma 1, and also we will have lemma 2. Let's say if we have a multipartite state, then FAB, if we have FAB, which act on trace C, rho ABC, equals, I mean, if the marginal is symmetric, then we would have the same symmetry in the original state. So they are equivalent. This is lemma 2. And we can prove this one from lemma 1. Just believe me, because we do not have enough time to go through it. Yeah. Yeah, so here it also works for not only FAB, but also FBC and also FAC.
So in the second line, you mean FAB of rho ABC?
Ah, sorry. Yes. Yeah, sorry for that. Okay, and then we have another one. If we have a symmetric state, this lemma is already known. If we have a symmetric state, then either it's fully separable or it's genuine multipartite entangled. If we have antisymmetric state, then it can only be fully separate. It can only be GME. Yeah, you can also believe me at this time point. Okay, now so I would like to make use of the figures. So let's say we have a symmetric state rho, which is a tripartite state. And if we assume that it can be from this network ABC, then we know that f a b trace c rho will equal to trace c rho. Correct? Because the rho itself is symmetric, so it's marginal. It's also symmetric under the flip operation FAB, according to our second lemma. Yeah, if you want to have a look. Yes. Yeah. It's not allowed during the exam. Okay. And not only for AB, not only for this marginal state, which act on, maybe we call it rho AB, not only for this marginal state rho AB, but also for rho BC and rho AC. Okay, as we know, we have the marginal relations between the original network state and the network state in the inflation. Okay, so in this case, it means that we have f, if we use f A, fb act on maybe trace, I will just write it in this way. We trace out all the parties except AB in the state gamma. We would have it equal to, correct? Because this state, as we talked before, it's just equivalent to the marginal state rho AB. Yes. So according to our lemma 2, it means that FAB gamma will equal to gamma itself. Correct? Yeah, it's another direction of lemma 2. Okay, all of those is based on that the state is symmetric, and we also assume this this structure, this network. Okay, so then continually we will have f b c prime, and also f c prime a prime, f a prime b prime, f b prime c, and also f c a. Okay. Whatever, no matter which one we choose, and we apply it on the state gamma, we will have the gamma itself. Okay. So then, I mean, then we know that we can use those bipartite flip operations to give us this flip operation f a and a prime. Yes, maybe, yeah, maybe it will be something like I'm not sure. Maybe f a, f b, f b, f b c prime, and f c prime a prime. Maybe we also need some, another copy. Yeah, I'm not. Yeah, so I'm not sure about that. Anyway, we can generate it from those. It's a group. It's a symmetric group. Yeah. So okay. So it means that for this state gamma, we will have f a prime gamma equal to gamma itself. Then, yes. So I will just write here because it won't be too long. So in fact, if we have a look at a and a prime in gamma, and also a and a prime in tau, we will have gamma a prime, this marginal state equal to tau a and a prime, because they have the same particles and they also have the same log channels. That's why, yes. So it means that if we apply f and a prime on tau a prime, it will equal to itself. according to our lemma 2, if we have FA prime applied on tau, it will equal to tau itself. Besides, we also have the marginal relation between rho and tau. So similarly, like here, like the argument here, we will have tau to be invariant under the flip operation FAB, FBC, FAC, and also FA prime, B prime, FB prime, C prime, and also FA prime, C prime. Okay, as we can see, so those operations, one is between A and C, one is between A and B, B and C. So we have the full symmetry in the inner triangle. Similarly, we also have the full symmetry in the outer triangle. And now, besides that, we also know that this state tau also have the symmetry between A and A prime. And then we can construct any the flip operator between any two parties because they are connected. Yes, here it's for the inner triangle, and here it's for the outer triangle. And then we have another flip to connect those two triangles. Then for any two parties, maybe C and D, no, sorry, for any two parties D and Z, we will have that the flip operator between them act on the state tau. It will give us the original state tau. Okay. According to the definition of multipathetic symmetric state, it just means that the tau itself is a symmetric state, multipathetic symmetric state. And as we can see here, for this bipartition, A, B, C, and A prime, B prime, C prime, this state is separable. Correct? So there are no entangled pair between the outer triangle and the inner triangle. And according to our lemma 3, yes. So then it means that it's not genuinely multipathetic entangled because it's separable for some bipartition. Then it can only be the first case. It can only be fully separable. So it means that if a tripartite symmetric state can be prepared in this triangle network, then it can only be fully separable. There can be no entanglement. Okay, so yeah. In the same spirit, we can prove that for any symmetric state and for any network, if we so it's like this. For any unpartite symmetric state, it can if it can be from some network with no unpartite sources, then it must be fully separable. And if we have an antisymmetric state, which can be from some network with no unpartite sources, then it cannot be the case because because it must be something like genuine multipartite entangled. Yeah. Okay, this is the conclusion for the symmetric state, and for the graph state, I think I do not have enough time. It's a little bit complicated, but the spirit is similar. We consider the interplay between the symmetry and the marginals, and for that we need to do the inflation such that we have enough details. Yeah. Okay. Thank you. Yeah.
acts on cats. Right?
Yes.
Because then you write FAB of rho, so you're only flipping the indices in the cats, not the bras.
Yes, that's true.
But this is not. How do you do physical instrument? This is not a physical instrument thing now. I can't physically just flip the indices in the cats and not bras.
So
when you say symmetric and antisymmetric, I'm kind of confused.
It's not a physical operation, but it's a linear map. You can define a linear map and see what happens when you apply it to this new matrix. It doesn't matter, I cannot implement it.
Okay.
Also,
Yeah.
does it also as soon as rho is Hermitian, like you also get it from the other side, and then you also get the full sandwich, like FAB rho, FAB is the same.
No, because then you won't have the property that you have plus
No,
and
no.
minus. You get two minuses and they're antisymmetric and it'll be plus. So you can't.
So then it means that if we apply identity plus FAB over 2 rho, it's a projector. It is equal to rho itself. So it means that the rho is in this subspace. Yeah, of course we can apply it on two sides, but it does not make any difference. So it just means that the rho is from this symmetric space. I mean, yeah.
Yeah, just for the last step, that already concluded that you cannot have genuine multipartite entanglement in the network. So just to see, so in the graph state is clear, I mean graphically already, no, in the T graph state, yes. There it's clear already graphically that it's not multipartite entanglement because you have two separate
Yes. Yeah.
triangles.
Yeah.
Now in the new case on the right hand side, it's not obvious, but this is what you concluded that this on the new state you can only have separable states, that this is.
Okay, I know. Yeah. So the conclusion is on the original symmetric state rho. I mean, if we assume it can be from this network, we cannot come to the conclusion only with this inflation because, as you have noticed, it's connected and maybe it's hard to see whether it's separable or not. That's why we need another copy, and we use the marginal relations as the bridge such that we can move from this inflation to this inflation and to have the separability. And then it helps us to come to the conclusion. Yeah. Yeah, you're right. If we only have this inflation, we cannot prove it. We need this one. Yes. Thank you.
So maybe I have a question. I was a bit curious about this graph state. Can you at least explain in very general terms?
Okay, so then I will just remove.
So I can imagine you have maybe similar conditions or similar.
Yeah. So for the graph state, in fact, we need more techniques. The graph state can be defined in this way. Let's say we have a square. Okay. 1, 2, 3, 4. Then we could have some operators x on 1 and z on the neighbors of 1. It's just 2 and 4. Okay. So similarly, we can have this kind of operator for 2, 3, and 4. Okay, I will make use of this question to explain more about the graph state. Then we would have x, z identity, yeah, and also 1z, x, z, and also maybe then it would be z1, zx, correct? Okay, now we have those. Sorry, I forgot to mention that they are just polymetrics.
Yes.
Yeah, matrices. Okay, and then we could have those operators. And if we consider the common eigenstate of them with the eigenvalue plus 1, then we would have a unique state. And this state is called the graph state of this graph. As we can see here, we already have some operators or stabilizers which act locally. Then we can combine it with the marginal relations and something like that. Yeah. Yeah. So we indeed need some stabilizers or some operators which act locally, and it can move along the network and goes to the contradiction. Yes.
Inflation, the relation to the marginals you can.
Yes. Okay. Maybe I can explain more. Sorry. Yeah. If we consider those two, and we make the product of them, then we would have x1, x identity, okay, which only act on here and here, correct? And okay, if we make the product maybe with 8, we will have minus y identity y x, which only act on here. It's 1, 2, 3, 4, and here it's 1, 2, 3, 4. Okay, now, I mean, if we have, so if we apply those two operators on the graph state, we know that the eigenvalue will be just a plus, because here it will give us plus, and here plus is still plus. So, but if we consider such inflation, so here it's 1, 2, 3, 4, 1 prime, 2 prime, 3 prime, and 4 prime. So here, if we consider the operator x1 and the x3, so I will just omit the identity. And we will also have y1 prime, y1 prime, and also x4, y3. It's just this one, but in this inflation. Okay, as we can see, the common part of them is 3. And if we call this gamma, and x1, x3, gamma equal to x1, x3, 0, we have those marginal relations, and also y1 prime, x4, y3, gamma equal to y1, y3, and x4, 0. Correct? They are just from the marginal relations. And okay, in the inflation, as we can see, they uncommute with each other. And there is one lemma. If we have a set of uncommuting operators, and they only have the eigenvalue -1 and +1, then the sum of the square of their mean values is more than 1. This is one lemma. So it means that here we would have x1, x3, gamma square plus y1 prime, x4, y3, gamma square more than 1. Okay. And we know that according to the marginal relations, we can replace it to be 0. And here we replace 1 prime by 1. And we replace gamma by 0. It should be more than 1. But we know that if it's such a graph state, we would have this one, according to definition, this one to be 1. This one, maybe before square, it's -1, but after square, it's also 1. So it's a contradiction. So it means that this graph state cannot be from this, this network. So generally, we have proven that if we have the graph state with no more than 12 parties, because people have classified all the graph states up to 12 parties. And yeah, it's easier to enumerate over them. Then it can never be from any, not only the same network as the graph for the graph state. It cannot be from any network with only bipartite sources. Yeah, this is our conclusion. Yeah, thank you for the question. Thank you. Thanks.
And where did you get, okay, because this symmetric thing, I kind of understand the intuition between the margins, and now how you move it around, with this different information. But here, where this condition come, or did you get the idea for the graph state? Because it seems very different.
This is the key point. So this is the key point, and it's from Otfried.
Ah, okay.
So
you knew this relation.
Yeah, Otfried has this result maybe 10 years ago or 20 years ago.
Okay.
Luckily, he remembered it.
Okay.